My name is Dallas Ballantyne. I'm from Minnesota. I'm a rising junior.
My name is Nikita Barati, and I'm a rising senior from Arizona.
Hi, my name's Karan Basine. I'm a rising senior from California.
Hi, I'm Eric Dahlman. I'm a rising senior from Kansas.
Hi, I'm Cody Garcia. I'm a rising junior from California.
Hi, I'm Paul San Giorgio. I'm a rising junior from New York.
Hi, I'm Jason Wren. I'm a rising junior from Texas, and our mentor was Dr. Timothy Urban.
So our mission background is that ICESat stands for Ice, Cloud, and Land Elevation Satellite. ICESat 1 and 2 are NASA satellite missions with the objective of measuring ice sheet mass, balance, and elevation, land topography, vegetation characteristics, and cloud aerosol heights. ICESat 1 was launched on January 12, 2003, and was in orbit until 2010. ICESat 2 was launched on September 15, 2018. ICESat 1 and ICESat 2 were launched on the Delta II launch vehicle from Vandenberg Air Force Base in California. ICESat 1 was deactivated on August 4, 2010, and re-entered the atmosphere on August 30th. The ICESat 1 orbit altitude was 600 kilometers, about 370 miles, in frozen orbit, meaning it will remain fixed essentially at the North Pole. Its velocity was about 15,434 miles per hour. It had a 3-year lifetime with a goal of 5 years use.
The NASA GLAS, or Geoscience Laser Altimeter System, on the ICESat mission had the primary goal of observing the polar ice caps and their impact on global sea level. The GLAS instrument operates with infrared and visible laser lights that eye-safe signals. The laser light pulses illuminate the Earth, enable it to measure the surface elevation of the polar ice sheets, topography, clouds, and aerosols with extreme accuracy. It measured the vertical distance from orbit to the Earth's surface 40 times a second, while traveling at 26,000 kilometers, or 16,000 miles per hour. Between ICESat 1 and ICESat 2, there was NASA's Operation Ice Bridge, where airplanes equipped with scientific instruments flew over the Arctic and the Antarctic. ICESat 2 is equipped with an instrument called ATLAS, or the Advanced Topographic Laser Altimeter System, which has a laser that can emit 10,000 pulses per second. ATLAS has 3 main tasks: to send pulses of laser light to the ground while determining where the laser is pointing, to collect the returning photons into a telescope, and then to record the photon travel time. The ICESat 2 spacecraft orbits Earth at 15,660 miles per hour and an altitude of 310 miles. Every 91 days, it completes 1,387 unique orbits. The mission collects a terabyte of data daily.
Mechanisms on board the satellite measure the round trip of laser photons as they depart from the satellite, reflect off the ground, and return to the receiver telescope. By matching those times with the satellite's location in space, the heights of Earth's surface can be determined. According to NASA, ICESat 2 will measure how much melting ice sheets in Greenland and Antarctica contribute to sea level changes, measure how ice sheets, glaciers, and more are gaining and losing masses in different regions to help researchers understand the mechanisms behind those changes. 3, to estimate the thickness of sea ice and monitor any changes. 4, and to measure the height of forests to calculate the amount of vegetation in a region.
For our project tasks, we used the training we received with Python coding from Lesson 2, and we aim to analyze the data from the ICESat missions by plotting land topography, roughness, and slope on graphs, and present the data in a video less than 20 minutes in length. We chose the White Sands area because it is a primary calibration site for ICESat 1. This site was chosen for its geophysical qualities, including its flatness and reflectivity, and it was also chosen for logistical reasons, as it is a domestic and secure site. Calculating slope and roughness values are important in that they help infer material properties of the surface being analyzed, and these factors may also have a topographic influence on waveform returns.
Our main approach to our project task was to create Python code that will be used to read and plot data. We used data from 3 sources: a DEM, or digital elevation model made from data from 2 aircraft LiDAR missions, ICESat 1 and ICESat 2. Using DEM data from 2003 and 2007, aircraft missions, which include latitude, longitude, and elevation values, we plotted 2-dimensional and 3-dimensional topographic maps. We also used color bars to illustrate the differences in elevation We then divided the map into grids and calculated slope and roughness within each grid. Roughness was created as a standard deviation of the elevation in each grid, while slope was calculated using a least square fit, which created a two-dimensional plane that best represents the three-dimensional scatter plot. The ICESat-1 data included 20 campaigns, or approximately months of data collection, with a time span from 2003 to 2009. This data differs from the DEM data considering that the ICESat-1 satellite collected tracks of data, not entire planes of data. These data files included all the parameters given in the DEM data, but also included skewness and kurtosis values. Skewness is the measure of how off the distribution of data is from the normal bell curve, and kurtosis is the measure of how sharp the peak of the distribution curve is. This allowed us to not only create graphs showing our calculated slope versus latitude and calculated roughness versus latitude, but also slope versus skewness, kurtosis versus roughness, and skewness versus latitude.
Since the ICESat-1 data is collected linearly, unlike the DEM planar data, dividing up the data was different as well. The data was divided into 7-point segments or groups of 7 data points instead of 1-kilometer grids. The roughness for each segment was calculated the same as the DEM data by computing the standard deviation of the elevations. However, the slope was calculated differently, creating a line of best fit using the 7 data values in each segment and getting the slope of that line. The ICESat-2 data were taken from the NSIDC, or National Snow and Ice Data Center database, and included data from 2020 only. ICESat-2 differs from both ICESat-1 and DEM as it has 6 lasers which create 6 distinct tracks of data. The data was also stored in an unfamiliar format to us, which was HDF5 files. Because of this, one hurdle we had to overcome was learning to navigate and read this file type. NSIDC provided example Python code which allowed us to figure out how to navigate this kind of file. Inside the HDF5 file, there were many sub-branches with their own data path names. These sub-branches included the 6 lasers, which each had their own elevation, latitude, and longitude data.
Given that we wanted only the data of white sands, the complete dataset had to be filtered as the ICESat-2 track went through much of North America. This was done by only using data that was within the latitude and longitude coordinates of white sands. We then used what we had learned from the NSIDC example code and from the SEAS Python Basecamp to take the filtered latitude, longitude, and elevation data from each laser and create plots of them. Because each data point was 100 meters apart, every kilometer of data was represented by 10 data points. The slope in meters over 1 kilometer was calculated using the curve fit method from the SciPy package. The roughness was just the standard deviation of a kilometer of data, and the slope in degrees was calculated by taking the arctangent of the slope in meters. These trends were then also plotted against latitude and longitude.
This video zooms in on white sands using Google Earth, showing the real location that these missions had studied.
Here we show the 3-dimensional DEM plots of latitude versus longitude with elevation as the z-axis, which were used to visualize the white sands topography in the years 2003 and 2007. These next 2 plots are 2-dimensional DEM plots. As shown, the points in the scatter plot are grouped into grids which are 1 kilometer by 1 kilometer in dimensions, and these grouping of the points were used to calculate slope and roughness within each grid. This last graph for the DEM data is of slope versus latitude, where the median latitude from each grid was plotted, and it demonstrates the flatness of white sands from the airborne survey data. This plot shows data from the 6 ICESat-2 tracks on the same plot as the 2 DEM maps together. And this map allows us to see which of the ICESat-2 tracks overlapped with the DEM data in terms of longitude and latitude coordinates.
These 2 plots show the average kurtosis values per segment and average skewness values per segment versus the median latitude per segment. This shows data of just one track, L3J0137, of the many ICESat-1 tracks we plotted. As you might notice by looking at the plot, it seems that kurtosis and skewness both spike at approximately the same latitudes. This suggests that kurtosis and skewness values are closely related and that those latitude points of the white sands might be less flat than the rest of the latitudes measured. These 2 plots show average kurtosis values versus the roughness per segment and the average skewness and versus the slope per segment. This is the data from track L3K1307. For the roughness versus kurtosis plot, there is a trend showing that the higher the kurtosis, the lower the roughness. This suggests that over rougher surfaces, the effective footprint is larger than when it is not as rough. We can conclude that since roughness and kurtosis are opposites, it would make sense that as one increases, the other decreases. For the slope versus skewness plot, as the skewness increases, the slope gets further and further away from zero. We have not come to the conclusion on why the plot has this trend. However, as our future work, we plan to take a closer look of the correlation between slope and skewness across all our data.
So for the ICESat-2 data, this first plot shows the 6 ICESat-2 tracks in a 3D coordinate plane. There are actually 6 tracks as pairs of tracks are very close together. The other plot shows the slope in degrees versus latitudes across all 6 tracks. We also plotted roughness versus slope and found that the greater the absolute value of the slope, the greater the roughness. Thus, as slope approaches 0, so too does roughness. Future work would also include comparing the data from the different sources where they overlap.
For our impression of the virtual Seas internship, there were both highlights and challenges. One highlight includes how we were able to get detailed training in both earth and space sciences, as well as Python coding, which will be very useful to our careers and our future paths. And we also got to hear from interesting and experienced speakers, scientists, and researchers that had overlapping research and expertise in the fields we were researching in, as well as they gave us new perspectives on different aspects of earth and space science. And we also got the opportunity to conduct real-world NASA research using satellite data. So with highlights, there were also some challenges. One challenge included efficiently and effectively making the best use of all of our skills. So some people were more experienced in Python, some people were more experienced in the earth science background. So working together to put our skills together and make the best project possible. And then also communication without meeting in person. So obviously we couldn't meet in person this year, but we were able to utilize platforms such as Zoom and Discord and Basecamp to effectively communicate and get our project done.
So before I was a Seas intern, I didn't know nothing about coding. I didn't know that much about earth science in general. I was able to gain a better understanding of coding and like how you can use it for like mathematical equations, how it can help make graphs for like science data and stuff from my satellites up in Earth's orbit. This internship has helped me in a way where I am more motivated and get my degree in aerospace engineering or aeronautical engineering, specifically in like spacecraft design and stuff like that.
So before I came to Seas, I've done research before, but it was more in a lab setting. And I've never really used coding and computational research and applied to research I've done before. So Seas gave me a new perspective on that and how earth science research and coding can go really well together to make some really impactful results and breakthroughs. So I think definitely the internship taught me a lot more about Python coding and improved my skills in that, and showed me in the future how a lot of jobs I can go into can work really well with the intersection of coding and use it to really make some impactful changes.
So for me, I've taken a few chemistry and physics classes in school, but earth and space science isn't something I'd really been exposed to that much before. So C's gave me a lot of resources for that, and I learned a lot. Also, I've had a lot of coding experience before with research too, but I hadn't really had the opportunity to apply it to something like with actual satellite data from NASA. So that was really interesting. And it kind of showed me that with my programming skills, there's a lot more paths than I thought before. Before I kind of it was pretty narrow. I thought you can become a software developer at a tech company, but now I know that the skills I have could also be used for conducting research in NASA, which is pretty cool.
Seas has contributed to my future education and career plans by showing me how important these NASA satellites are to our everyday lives. This encourages me to want to take an education and career that deals with this type of work we did here and with satellites. Also, the new skills I've gotten in Python open so many opportunities for me.
This opportunity has helped me decide how I want to work with NASA. I learned how to code in Python. This has jump-started my career with data analysis, and I now have a solid base to jump off of into my college years.
For me, going into this internship, I already had some coding experience working on the robotics team, but I didn't really learn a lot about astronomy, earth science, or data analysis at all. So being able to combine something I'm familiar with and something I'm not was really cool and helped me realize that there are a lot more coding career paths out there more than just robotics and like a software engineer.
Before I started this internship, I had no idea how much NASA viewed our own Earth as a whole. You always hear about the Apollo missions, the Voyager missions, all those really big ones that go out further into space, but you never hear that much about the ones that observe the Earth as a whole. So that really helped broaden my horizons. NASA isn't just about space, it observes the Earth so much as well because it's part of our solar system. This has helped broaden my horizons very, very much, learning new Python coding skills, the massive one, learning about earth science, meeting so many great team members, getting to view so many speakers and people that work at NASA and working with actual NASA data and scientists was an amazing experience. It just finally helped me choose on my degree, which is aerospace engineering.